Today we're going to talk about lab errors and making lab measurements. So the topics we're going to talk about are the measurements themselves and accuracy versus precision and the various types of error that we can encounter when we're running our labs. Okay, and primarily one of three choices. Okay, it's going to be either random error, systematic error, or hopefully we won't have any of these, but also human error. First off, all measurements are made with instruments and read by a human being. So your answer is never going to be exact. No matter how good your instrument is, it's always going to be subject to a level of precision. For electronic instruments, the precision is usually printed on the instrument, or what we'll probably use is the smallest digital increment. For example, a digital balance reads 402.07 grams. The precision then would be plus or minus 0.01 grams because that's the smallest digital increment that we could have. For manual instruments, okay, the precision is going to be the smallest increment printed on the meter stick or graduated cylinder or whatever the instrument happens to be. For example, a meter stick, the meter sticks that we have in the lab have millimeter increments, and therefore they have a precision of a millimeter or plus or minus 0.001 meters. Okay. In some instances, the person reading the measurement may feel confident about estimating to a smaller level of about half that increment. So you could have 0.5 of a millimeter or 0.0005 of a meter. That level of accuracy is not really going to be needed in this class, and I personally prefer erring on the side of less precision than you actually have. In terms of the terms accuracy versus precision, okay, a measurement is determined to be accurate if the average of the measurements is going to be close to the exact value. You really want your measurements to be accurate. Okay, if they're not accurate because of miscalibrations, then you're really getting the wrong data. Okay, and a measurement is determined to be precise if the variations between those measurements is small. Okay, normally we can relate precision to how many decimal points does the equipment read. Okay, those two terms are similar, but they do not have to correlate. You could have a situation of high accuracy but low precision. Okay, like in the case of the third target, okay, your accuracy is pretty high, but your precision not quite as good as the first case. Okay, you could also be precise in that your equipment is reading very well, but it's miscalibrated or there's something else going on with your experiment such that you're not accurate, like in this second case. Okay, it's important to note that all of these terms of accuracy and precision are really relative terms. Okay, is the first example of the target, is that accurate? Yes, it is pretty accurate, but I could be even more accurate depending on the piece of equipment that I'm using. Okay, it's all going to be relative. Which one's more precise? Okay, is A more precise or is B more precise? It's pretty close. I would actually think maybe A is a little more precise. In the case of D, that looks like very low precision. So those two terms don't have to correlate with each other, and it's important to remember that they're relative. Okay, the question should always be, is this equipment or is this procedure more or less accurate, more or less precise? Okay. Random error is exactly as the name says, okay? It's the error can be either higher or lower than the actual value. Okay, you cannot totally control most random errors. You can only reduce it. Okay, for example, when you're reading the meniscus on a graduated cylinder, your eye must be at the same level as the meniscus, but you're really judging it. Sometimes you'll be a little higher, sometimes you'll be a little lower. You're equally likely to be high or low. Okay. Or another example is vibrations on the lab table or wind currents are slightly affecting a balance scale, forcing it to read slightly higher or slightly lower at the instant that you're reading it. Okay. Systematic error, however, is not random. It's usually due to a poor assumption in your experiment design. And in general, you can fix or avoid these types of systematic errors. There are some systematic errors that you can't avoid, but one way of determining whether an error is a systematic error is, are your errors always high or are they always low? For instance, when we were measuring the room, okay, the length of the room with a meter stick will always actually measure longer than it actually is, because we never could get a perfectly straight line. It always zigzagged just a little. Okay, and that way it'll always read on the high side. Other examples of systematic errors are miscalibrations in equipment, miscalibrated scale. So 0 is not an empty scale. That's an example of an error that can be fixed simply by calibrating it. One example that you can't fix is if you're measuring something, the volume and mass of an object, okay, of a liquid. Between the measuring the volume and measuring the mass, there will always be a slight amount of evaporation, and you can't do anything to avoid that evaporation. But it will always result in less mass than there was when you measured the volume. Okay. The last error I hope to never really see, and that's human error. But we're all human, and mistakes are going to happen, so that's okay. What is not okay is using those situations, those measurements in our lab anyway. Okay, human error is always fixable, and for the lab to really count, it must be fixed. Okay, any trials with human error, you spilled the beaker, you put the apparatus on setting 2 instead of setting 3. Okay, those trials simply do not count and are usually discarded. If there's something to be learned from the human error so that we don't do it again, maybe it's worth keeping in there and talking about it in a discussion section. Okay. However, human error is never a valid reason that an experiment fails. Okay. Those are things that we can fix, and we must fix them while we're doing the experiment. Okay. Human variability, okay, that's a different story. Human variability in terms of like reaction times, reading the levels of our equipment, okay, those are what we factor in as random errors. And those we can't really do much about, again, because we are human. Thank you.